Okay, welcome back Physics 20s to our next lesson in Chapter 8. This is going to be looking at 8.2, which is looking at properties of waves. Now, from seeing waves in life experiences like water waves and what we covered last lesson, you probably have a bit of idea for how they work. But I just want to recall some of those things from last lesson and emphasize the difference between the particle movement and the energy movement. So we had two types of waves. The first type was a longitudinal wave, and that was created when the particles were moving in the parallel direction to the energy. So say we take the end of that material, and this is just showing the particles of that material, and we shake the end of it in this direction, right? There's going to be some compressions and rarefactions, and they end up looking like this. So here, due to that movement back and forth, is a compression, and then here where they're in a spread out phase, over here would be a rarefaction. Right? And that's easy to see on like a spring or a slinky, that you compress it and let the compression travel down. The energy is going to be going in this direction. The particles are moving in this direction. They're parallel to each other. If you want to make a transverse wave, which was the other type, you're going to move the particles or the material there up and down, and then the energy is going to go side to side. So they're going to be perpendicular to each other. So we shake this up and down like that, and then we get a wave looking like this. Again, the movement of the particles are like this. The movement of the energy is like that, okay? Now I want to emphasize here that the energy moves much further than the actual matter or mass does. The matter, the mass here is just moving back and forth, but it's pretty much staying in the same spot. So the matter's not moving a large distance. What's moving a large distance is the energy that gets transmitted through this material. So energy can transmit a far away, and we're not transmitting the matter. I think a good example of this was when I was at Rabbit Hill, and there's this tow rope that goes all the way up the hill, which is basically this big long rope, and I decided to put a wave through it. So I just shake the tow rope up and down, and it makes a wave kind of like that. Probably not that big in real life, but you kind of get the idea. And that was caused by lifting and pushing the rope back down, and it makes this wave pulse. And although the rope moved only up and down right here, that energy that I put into the rope transmitted down all the way up to the top. So I saw the pulse go from there to there to there, and it traveled the whole way. Just want to reemphasize, energy is what's being transmitted. Matter is not moving very much at all. So when we look at this water wave now, I think it's common to think that the water, the amount of water right here, is actually going to move all the way to over here, but that's actually not the case. The water particles here are going to be moving, they kind of more a little bit complex. It's kind of a mix of a longitudinal and a transverse. It kind of just rolls, so it kind of makes this circular motion. But it's going to move like that, which is going to cause the next particle to move like that, and the next one to move like that, and the next one, and so forth. So this water particle causes energy to be transferred all the way across this pond, but the actual water particle does not move that distance. So I just want to make that clear. Now we're also going to use this diagram to look at some of the characteristics and descriptions of waves, so we can use those to describe wave properties. So first of all, it's the circular wavefronts coming from a point, this point right here where the ball is going to be creating the waves, and this is called the point source of those waves. It'd be similar if you had a speaker which was making sound coming out from that position. Now we can see also these rings coming out from that point source, and they're getting bigger and bigger and bigger. What we're going to call those is wave fronts. Okay, and what those represent is where the energy of that wave is reaching all at the same time. So it all starts at this point, and then it travels in a circular direction outwards, and it's going to get to here the same time as it's going to get to here and get to here. And it's really easy to visualize that on a pond, as we can see that's where it looks like the ring is moving. The next thing we're going to include in diagrams is rays, and they look like this, and it's going to be showing the direction that that wave is moving. So it starts at the point source and moves outwards, and it's going to be 90 degrees to the wave front. So we can see here it's 90 degrees, 90 degrees, 90 degrees, 90 degrees, the whole way across. Now this picture kind of distorts it because it's looking at an angle, not directly over top, but hopefully you can still see that. It's not just in that direction, any direction that the energy is moving. So I could draw a line right here, same thing, 90 degrees to that ray is the wave front. So these arrows are called rays. All right. Now the last thing I wanted to point out about this diagram is that right close to the point source, we have quite circular wave fronts here. We can see a big amount of curve in those wave fronts, But as it gets further and out, and the circles basically start to get bigger and bigger, if we're looking at the same area over here, these pretty much seem to be just in straight lines. So if we're not looking at a wave right from the point source, I might draw the wave fronts coming in as straight lines with a ray moving like this at 90 degrees to those wave fronts. Okay, now let's look at some diagrams to see how waves are going to act and what their properties are. First one we're gonna look at is reflection, which is just bouncing waves off of stuff. And you've been familiar with this anytime you looked in a mirror. This is when light waves are gonna bounce off the mirror, and then you're gonna see them after they've been bounced. So this is gonna represent my mirror down here, or our reflective surface, and I'm gonna take a wave, and I'm gonna show the ray coming into that surface. Now it's going to bounce, and the most important part to understand is the angle that it's going to bounce off at. Now it's common for students to think we're gonna measure the angle to the mirror or the surface here, but that's not always a straight line. Sometimes it's gonna be curved, so we are not gonna measure it compared to the surface. We're gonna measure it compared to something called the normal line, which I'm gonna draw right here. And this is 90 degrees to the surface at the point that the ray is going to hit it, or that the wave's gonna hit it. So I'm gonna put a point here. That's where the wave is hitting the surface. And the normal line is 90 degrees to the surface at that point, right? And so we're gonna measure the angle of the wave to that normal line. So I'll erase the one we don't and show that we measure here and here. Now the one coming in is called the angle of incidence. A symbol just for angle and I for incidence, which is the incoming ray. And then the one going out is the angle of reflection, right? And it turns out if we look at these, they are the exact same number. The angle of incidence is going to equal the angle of reflection. And you just need to remember to measure that from the normal line. All right, now this doesn't matter what type of wave. We could have a light wave coming in and it's gonna reflect back out the exact same way, or we could have a water wave coming in and reflecting back out in the same way. So kind of similar to what I said before, this is gonna represent those wave fronts coming in kind of as straight lines because we're not close to the point source. Now we'll look at a demonstration. I did some filming of this with a water table. So I'm gonna just play this clip right now.
So what you're looking at is the water table, and you're looking below the water table. I have a dowel in the water table, and I'm able to make a wave like this. And because I'm shining light on it, you're able to see that wave travel through the water. Okay, reflection. I have this barrier, I've just moved it for you, and it's set up approximately at 45 degrees. Let's send a wave at it. Do you see the reflected wave come off and move in an opposite direction across the water table? It's moving at an angle somewhere around 45 degrees. I'll send successive ones. Okay, let's have a look at that.
Okay, so in this demonstration, they're shining a light down on water and then looking at the shadows on the table. And this allows us to see how the waves are moving because of how they make bright and dark lines based off the curvature of the water. But anyway, we're just looking at how the waves are going to be moving. And so I took a picture of it here and we can see the movement of the waves and how they're going to reflect. So first of all, I'm just gonna put the barrier right here to show that that's what that shadow is represented by. And I'm gonna use these light lines to kind of show where we see the wave there. So I can kind of see that, that vertical line here like that. That's gonna represent one of the wave fronts coming in that they created with a dowel. And when he was doing this in succession, there was lots of wave fronts coming. So I'm gonna draw one, say was back here. Here's our next one that we can see, and here's our other one that we can see kind of in that vertical direction. But when they bounce off of that barrier, they're going to reflect. And so we can see those other lines represented like this that I put in red, and the ones that have reflected off of that barrier. Now, if we look at those compared to each other and we draw a normal line, we can see that the angle of incidence is equal to the angle of reflection. And because he sent them in at 45 and they're coming out at 45, it looks to be approximately 90 degrees. Now, this does not apply just for straight mirrors or straight surfaces. You could have curved ones like I mentioned from before. That's why we don't want to measure the angle of incidence compared to the mirror. We want to measure it compared to the normal. So say we have this curved mirror and we're going to shoot some rays of waves. Let's say this water waves moving at it, and what's going to happen. We can predict what's going to happen by drawing those angles. So again, we do not want to measure compared to the mirror because the mirror is angled. We do not want to do that. we want to compare it to the normal line. So I'm going to draw these normal lines, and you notice they're not all parallel to each other because they're at 90 degrees to the mirror. They're not 90 degrees to like the page or anything like that. So I'm going to draw this 90 degrees to the mirror at that point, 90 degrees to the mirror at that point, and to the mirror at that point, or the barrier or whatever these are bouncing off of. So make sure you draw the normal 90 degrees to the surface. That's a common mistake on tests. And now that we have our normal lines, we're just going to take the angle that it came in at, angle of incidence, and draw an arrow coming out so that the angle of reflection is the same like that. So we say angle of incidence is equal to angle of reflection. Those are going to be the same. Angle of incidence is equal to angle of reflection. Those are the same there. So I'm just going to put angle I, angle R, angle I, angle R. Now for the middle one, it comes in right at the normal. It's like straight on it. So there's no angle between that and the normal line. It's 0 degrees. So it comes in at an angle of 0 degrees and it's going to come out at an angle of 0 degrees to the normal. So it just comes straight back. And you can see that all of these rays are now coming to one point. They're going to be focusing in on this point here, which is called the focal point. And so if you're drawing a diagram like this, make sure you show them coming to one point. And if you were asked to draw the wave fronts on this, because I drew the rays, which is easiest to predict where the energy and where the wave's going to be going. But if you have to put the wave front, it's not too hard. We just show 90 degrees to the rays is what they're coming in at, like this. Now to make it a little bit more clear, I'm just going to draw it on each individual ray now that they're coming together like that with those wave fronts. Okay, and they all come to that center point. We're gonna look at a demonstration of this as well, where the water is coming to this curved barrier.
Okay, what I've done now is set up a parabolic reflector, and I'm gonna send my same plane waves at the parabolic reflector. I'll send a single one. I'm wanting you to see them focus to a point. The waves reflect and focus to a point. Here come successive ones.
Okay, so I've taken another picture of that, and hopefully we can kind of analyze that and look at some lines here. So first of all, the rays are coming in at the same direction. These are coming straight at the curved surface. Now we can see this line here is kind of representing the wave front, or the wave that you would see in the water, and then those arrows are just representing the direction that they're moving. Now I'm going to show with those arrows where they're going to hit the curved surface like this. And same as I did in the diagram before, I'm going to take that normal line, which is going to be 90 degrees to the surface, and draw it coming out at the same angle that it went in. Same thing for the one that hits directly flat and the one that hits lower there. It's reflecting at an equal angle that it came in at, so the angle of incidence equals the angle of reflection, and it's to that normal line, which is 90 degrees to the surface. So I'll just put that in here, angle of incidence, angle of reflection, angle of incidence, angle of reflection. Those are going to be equal to each other. And then our normal lines are 90 degrees to the surface. And then hopefully you can also see this area right here is a lot brighter. We can see that's where the wave is a bit getting focused, and that's the focal point, which pretty much matches our diagram, the lines that we've put on here, pretty much that same bright spot. So hopefully that makes a little more sense seeing it in real life. So next we're going to look at bending waves, and the first way we can bend waves is called refraction. And you might have seen some pictures or maybe seen a demonstration of this in previous schooling where it looks like you can bend a pencil just by putting it in water. But what's happening here is the light is being bent by that new medium, by being in that water. And so when light travels through water, it's going to be going at a different speed than it was going through air. When it goes at a different speed, it's going to cause it to bend from that original ray. So we're going to look at some demonstrations of this first, and then I'll do a diagram.
Okay, now what I've done is put a piece of glass in the water. Now the purpose of that is it changes the height of the water, and that means that the wave will travel at a different speed. It's going to slow down as it goes over the piece of glass. And when waves change their speed, they bend. So this is called refraction. And I want you to notice the wave come along, hit the glass barrier, and bend towards the normal. I'll explain that term later. But it bends inward on the glass. Here come successive ones. Okay, what you saw there is called refraction.
Okay, so hopefully you could see there in the middle, you can rewind it if you like, but in the middle of that square, you can see that it was no longer a straight line, but it was going up and then it bent like this because it was traveling slower over top of that glass. I'm gonna show a diagram here of how that would look if it was going through water, kind of similar to the cup. So this is gonna be like our water. Imagine like a fish tank. That's what we actually use to demonstrate it if we were in class. And I'm gonna bring a ray in here. Say this is a ray of light, and it's going to go from air into that water. So I'll put here, just label it, that this is our air, and this is the water. And the light is gonna be traveling slower in the water. So if it's coming in at an angle, this is gonna cause it to change the direction that it's heading in. Now first, it's important to note that when it changes mediums, it's also going to reflect. So I'm just gonna draw that first. It's gonna reflect off the top of the water, just like we saw from the last slide, with the angle of incidence being equal to the angle of reflection. So let's just say that's coming in at about 45 degrees, and then it's reflecting out at 45 degrees, just bouncing off the surface. But when it changes that medium, if it's not like a hard mirror and it can actually pass through here, it's going to go into the water and it's gonna do that. It's gonna bend. It's not traveling in its same direction. It's going to bend towards the normal here. We can see this angle is gonna be less than 45. Depends on the density of the water, but let's just say that's 25 degrees right there. So I'm gonna put here down at the bottom, if it goes into something slower, it's going to bend towards the normal line. That's how it's going to bend. But now as that ray hits that edge of the water and it's going to go back into the air, we're going to have another bend. So again, imagine this is like a floating fish tank, and now it's going to be coming out of the tank and it's going to be going back into the air. Now it's going to be going into the air which it was traveling faster in. So it's going to be going from slow to fast, and we're going to see the opposite bend. So I'm going to draw the normal line. It's coming in at this angle. Now it's going to be the same angle as it was at before, so 25 degrees there. But now because it's going faster when it goes into the air, it's going to bend away from the normal. So I'm going to put that here, away from normal line right there. And it actually is going to match the same angle that it had when it started. So if I slide that first arrow down to here, we see that they're matched up, so that this angle to the normal now is back to 45 degrees. So I'll just put that back to that point. Notice that when things are being reflected, they have an equal angle. When they're in the same medium going at the same speed, they have the same angle. And when they're traveling slower, they bend towards the normal to a smaller angle. And we can see also that it got bending away from the normal when it went back to going faster. I think it can sometimes help to look at the wave fronts here. So I'm gonna draw the wave fronts in green here for this ray. Now if I'm drawing them like this, we notice right here, what's gonna hit the water first is that left side of the ray. And kind of think of that if it was like you were moving this ray, this straight line, and it starts to slow down on that side, it's gonna cause it to bend. So this side's gonna be going fast, this side's gonna be going slow, so then it's going to end up going, I'll switch it to orange now so you can see it a bit better. It's gonna be going like that because it's slowed down on that side. And then when it goes to speed up, I'll show it with orange here again. This side now exits the water first and starts to speed up. So it's gonna go quicker there, slower here, and that's gonna cause it to kind of straighten back out. So that might kind of help you understand with that bending there, including the wave fronts. Now there is another way that we can bend waves, and it's by passing it through an opening, which seems weird. You'd think that it would just pass through an opening and be unaffected. But say we're sending these water wave fronts at a barrier, kind of like we saw in the video, and they're coming along, you'd kind of expect them just to pass through and continue on like this, but that's not what they do in real life. In reality, they do this. They come out as circular wave fronts and seem to bend around that barrier like this. So you'd think it wouldn't reach anywhere over here, but because of that bending, it's going to. So how the heck is that happening? The explanation that I'm going to use is Huygens principle, which says that in a wave front, every part of that wave is acting as a point source. So I'm going to draw some particles here and say that's the particles of water in the wave. And he's saying that those are acting like a point source. So if I was going to tap my finger on the water right there, it would make circular wave fronts at all of those spots. He said if it's got every single particle making all these circles together, they're going to be kind of overlapped until it just looks like a straight wave at the start. So that's how the wave is going to be being created. So that wavefront is made of a whole bunch of circular point sources of waves. Now that works for showing all these lines because that's the sum of all those circles. But as soon as you wipe out all the other circles, which I've kind of shown here, we just kept that one in the middle here, then that's the only one left making that wave. And so we can see that that curvature is going to match the curvature of the circle, and that's why we get a circular wavefront coming out on the other side. So now let's look at that happening in real life.
Okay, so now we're looking at a third thing that waves can do, and this one's called diffraction. You might think of it as bending around corners. So refraction was bending. This is a different type, diffraction. It's bending around corners. As I send the plane wave to the space that you see there, watch for a curved wave to come out. Here come successive ones. Okay, I want to adjust the gap and see if it makes a difference. Let's widen that gap and see if it, in fact, still gives me a curve, and if the curve is more or less. Hopefully you see that the curve is less, that the bending around corners is better when the gap is smaller.
Okay, so I think that shows it pretty well that you can see it bending around and see that circular wavefront. And he also brought up another point that's just good to look at how the size of the opening is going to affect that amount of diffraction. If we have a large gap and we're passing wavefronts through here, it's going to bend, but not that much. So we might get a curve kind of looking like this. I know it's not quite as good as those other diagrams were, but we get some slight curving. But if we're going to draw this so that they're much closer together, it's a smaller gap, kind of like this, we're going to get much more bending. So we send those wave fronts at it, and it's going to bend much more significantly. Kind of looks like the Wi-Fi symbol. So some students often think that it looks like. We get more bending for the smaller gap. Another relationship with what's going to bend more, going to be the wavelength. And oddly enough, longer wavelengths are going to bend more. So I'm going to draw long wavelengths here. Let's put it in red. So it's a pretty big gap between those peaks. And then when they bend, they're going to bend quite a bit around that. I'll draw it even more there, bending like that. And I like to think of this as if you talk through a doorway. So say you're standing outside of a room and you're yelling at the doorway, use this small diagram to represent that as the room. And the person talking out here is sending sound waves with pretty long wavelengths into the room. They pass through the door and they're able to fill up the room and people can hear you inside of there. However, if you're going to take light, so I'll just put this with orange here, and shine a flashlight directly through there, which is a much shorter wavelength, it's not going to bend and light up the room. It's going to maybe bend the tiniest little bit, but it's pretty much just going to hit the wall. If it was a really tiny gap, it would bend significantly, but for a door frame that big, it's not really going to have any effect. So the shorter wavelength, which I'm going to draw kind of like as a longitudinal wave here, just to kind of stay the same as the red diagram. If it's a lot closer together, shorter wavelength like this, we're not going to get as much bending. You might still get some, but it's not going to be as much. So those two relationships, increase the size of the gap, get less bending, decrease the size of the wavelength and get less bending as well. Now I know there's been a lot of properties in this video. We're just going to look at one more thing, which is showing how waves are going to bounce off of a solid medium, like when they're sent down a string. So first here I have a string, and this is supposed to be a fairly light string over here, and then this is a more dense string. And so I'm going to send a wave through that string, a transverse one, and you're going to see how it changes when it goes to a different medium. So it's going to slide along there, and it's the pulse, and then it's going to have this effect. So it's going to pass through this thicker or more dense string is going to have a wave get sent through it as well. And it's going to be on the same side. But once that lighter string bounced off of that kind of change in mediums, when it went to the more dense string, it's going to bounce off and come back through that lighter string on the bottom. So this is kind of like flipped it. It's an inverse. So we're going to call this one the transmitted wave. Transmitted, because it kind of passed through into the next one. And because it's on the same side as that it started, it's called erect. It stays on the same side. But the other one, that when it gets flipped and comes back through the reflected wave, that got flipped on the other side. So this is inverted when it comes back. And we can see it moving off back in that direction. Now we're gonna look at if you go to a lighter string. So I've started with kind of a medium density here in yellow and then going to a very thin white string. So it's gonna move along, it's gonna hit that change in mediums, and then we're gonna get this. It stays the same side or stays erect on both types of waves. The transmitted one here is still on top, and the reflected one is still on top as well. So reflected right there, and they're both going to be erect. All right, so we can see they'll move off in those positions still on the top. And I would sum this up in a diagram that looks like this, where if we start with a wave pulse going in this direction, they're going to make. All right, when it hits that barrier, if it's going to a more dense one, it's going to stay erect there. I'm gonna draw this kind of being a bit thicker, like that. But when it bounces off, it is going to become inverted when it comes back. If it goes to a lighter or less dense string, it is going to be transmitted along the top. So no matter what type of medium it goes to, it's always going to be transmitted on top or erect. But the reflected one, if it's going to a lighter string, is going to come back on the top or be erect as well. And that's all we have. I know it's a lot of stuff to memorize, and it's a lot of just theory. There's not really much calculating for this section, but just kind of knowing those properties of waves, as there can be lots of theory questions on that. So I hope it made sense for you. Again, since it's kind of harder to know if this theory is making sense, let me know if you have any questions. Join me in the meet if you would like, and I will see you in the next lesson.